This is Jim from RV4x40.com. Welcome to the channel today. We're here to try to show you some things we've learned about RVing by living full-time in an RV, and maybe give you some tips and also show you some of the places we've been that may also give you some ideas for things you can do with your RV life. I've gotten a lot of questions about batteries and how you select them and what the different types are and what the trade-offs are. And I think there's a fair amount of confusion out there, especially when you look at the cost of some of the options that are out there. So I wanted to kind of go through that today and give you a presentation that I put together that talks about the batteries and how to select them and what the different trade-offs are, and at least the major types of batteries you're going to run into. We're going to start today with covering some basic terminology. It's important to understand a common reference point. And so the most important and basic element of a battery is actually a cell. That's a device that's capable of creating electric current from a chemical reaction. Batteries are then composed of multiple cells. They can be connected in series for higher voltage, for parallel for more current, or a combination of the two for an increase in both. A rechargeable battery is simply a battery that's capable of reversing the chemical reaction, and it does that by using an external current source to force current back into the battery. The charging process is not perfect. It will take more energy to recharge a battery than the battery has delivered. This is called charge efficiency. It'll be somewhere typically in the 95% range, but it's not going to be 100%. And the number of times a battery can be recharged is limited. They do not have an infinite life, and really the more you use them, the quicker they wear out. Cycle life is generally defined as the number of discharged charge cycles, as long as the remaining charge is still above 80% of the original charge held by the battery. You can use them beyond that point, but it's considered an economical point and end-of-life characteristic. There are some electrical terms that we're going to be using. Volts, that's the forcing function that pushes the current around the circuit. Amps is the current or the amount of energy that's moving around in a circuit. And then watts is the amount of power that's moving around. One thing I have to address is that people will commonly tell you that watts equals volts times amps. That is only going to be true in a DC circuit 100% of the time. It will be true in some AC circuits, but they are more complicated, and sometimes multiplying volts by amps only gives you volt amps, not watts. Watt hours, simply the number of watts moving around times the number of hours that they're in motion. Amp hours, the same thing, but it's the number of amps moving around. And there are a couple of different types of batteries you run into. Starting batteries, which are the ones you're used to having in a car or truck, whatever, and they're designed to start your car, so they deliver very high currents to the starter motor for fairly short periods of time. It's measured in seconds usually. And they can be easily damaged by a deep, slow discharge because they're not ready for that, they're not built for that, and you'll find them rated by cold crank amps. The other type are deep cycle batteries. They won't deliver as much peak current, but are designed for deeper depth of discharge over multiple cycles, and they handle that pretty well, and they're rated by amp hours. Depth of discharge is a term that is about the amount of stored energy remaining, and it's expressed as a percentage of the original charge. So, common question, and we see this a lot: how do I know how much battery capacity I need? Well, you answer that question with another question. What do you want to run, and how long do you want to run it before recharging the batteries? For that, you really need to do an energy audit of everything that will be powered from the battery. And here's a typical energy audit. It's a fairly short one if you have a motorhome or an RV of some kind with a lot of different ways to use electrical energy inside of it. For example, you might also have 12-volt lights that are running. This is strictly looking at the AC appliances for right now, but the concept is the same. And those are some typical devices you would find and the amount of power they use. And it's not all that important what the power is as long as the system can deliver it, but the time that they're in use becomes a very important parameter. Blender, probably not used very often. I put in 4 minutes in the course of a day, and you're interested in hours, so that's 0.07 hours. And you can look at the rest of the number: coffee maker for 30 minutes, microwave for 4, phone charger, and an LED TV. And you can see that the LED TV, while it only consumes 150 watts, the microwave is maybe 10 times that, but the energy used by the LED TV, because it's on for 6 hours versus maybe 4 minutes, is 900 watt hours versus 100 watt hours. And that's what you're going to use in a day. So You want to take this and then go through your entire list of appliances and connections, get all that added up to get to the total number of watt hours you're going to need in the day. So we've looked at AC loads, and the question is going to be, how do we get that back to a 12 volt or some other voltage battery? And you're going to have an inverter somewhere in your system that's going to take care of that for you. Its input can be 12, 24, 48 volts depending upon the system design. And we know we need 1747 watt hours per day of AC power. Our inverter charger is going to be about 95% efficient, and that will get us up to 153 amp hours per day we need from the batteries. Yeah, what? How do you get from watt hours per day to battery capacity? Let's look at that. We know we have 1747 watt hours per day delivered by the inverter, and we know the inverter is 95% efficient. So we divide our 1747 by 0.95. That gives us 1839 watt hours per day consumed by the inverter or into the inverter from the battery. And if that's at 12 volts, it might be slightly higher, but we'll use 12 volts. That gives us 153 hours per day required from the batteries to meet the needs of our energy audit. Once you figure that out, you're going to start looking at what batteries you might want to use. And there are two main choices. There are lead acid batteries, and then there are lithium iron phosphate, or LiFePO4, or LifePO, as they're commonly called. Lead acid is further subdivided into three main types: flooded lead acid, or wet cells, absorbed glass mat, or AGM, or gelled electrolyte, or gel cells. These last three all have some things in common because they're all based on the lead acid chemistry, so they have several features in common. First of all, depth of discharge should be limited to about 50% for rated life. A 200 amp hour battery should really only be used down to about 100 amp hours of capacity. You can use it further, but the further you use it and the further you use capacity out of it, the more you shorten the life, with the potential, if you run it down to zero, of completely damaging the battery and making it unusable. If you use it less than 50%, you will get longer life out of the battery, but this is a number we're using for talking purposes. Lead acid batteries are heavy, and they have to be mounted where ventilation is available, and that does include the AGM and gel cells as well. They are subject to relatively rapid self-discharge, even if they're not connected to anything at all. And capacity is reduced by high discharge rates, called the Puchert effect. We'll talk about that in a minute. And charge and discharge curves both have significant slope to them, which gives them an interesting characteristic when you use them in the real world. Puchert's effect, or Puchert's law, was found by a German scientist back in 1897, not long after the batteries were invented. This is the lead acid technology that's still in use today. A capacity of a battery is rated in how many amp hours, but you will find the available capacity changes drastically based on the ampere draw of the battery. This battery is a 120 amp hour battery, and at low current you would get 120 amperes out of it. But the current draw would have to be very low, only an amp or two to do that. And now, as you pull more and more current out of the battery, you'll find that it gives you less and less total capacity. The top numbers, 1.08, something for an AGM battery, and maybe down to the 1.12. The ones in the middle would be for a gel cell, and the ones at the very bottom would be for a flooded wet acid battery. So you can see, with a really not very good flooded battery, and you pulled 50 amps out of the battery, instead of getting over 2 hours that you would expect from a 120 amp hour battery, you're only going to get about 20 amp hours out of it. So this is a big drawback to lead acid batteries, particularly when you use them in high load applications like driving an inverter, where you might be pulling 100, 200, 300 amperes out of the battery to run the inverter when it's running up at its rated load. The discharge curve looks like this. The lead acid battery starts to lose voltage about as soon as you start pulling energy out of it. And it will discharge down to under 10 volts to the time it's completely discharged. You can see the lithium ion battery has a much flatter curve and holds its voltage up very well until it gets up to about 90% and even 95% for 12 volts. So they're much more usable energy at the tail end of the curve. The charging curve for a lead acid battery is very interesting because the typical charger will start off with some constant current mode when the battery is discharged, and it'll have some limiting voltage, which it'll get up to, which is set on the battery somewhere around 14.1 volts. And so when you first start charging the battery, you get a lot of current flowing, whatever the charger is set up to do. But as you approach that final voltage, all at once the battery simply will not accept the current. It basically is fighting back to the charger, and so you'd take a much longer time to get the last 20% than it took to get the first 80%. The practical effect of this is that you have to run solar panels for a much longer period of time to get a lead-acid battery charged, or you have to run the generator for a longer time to charge it through a converter. At the end, when the battery is fully charged, it goes into a float state, and that is simply to make up the energy the battery is going to lose by self-discharge, even if it's not driving anything at all. Flooded lead-acid batteries, in detail, they are named that way because the electrolyte is a liquid solution of water and sulfuric acid. They were invented back in 1859 by a French physician. There were other technologies around at that point that had made batteries, but he's the one that came up with the current system of lead and sulfuric acid being the battery combination. It's currently the lowest initial cost, and it has good life cycle costs if you maintain them and if you get a decent quality battery to start with. But they also take the most maintenance. They are subject to outgassing, and that's due to the charging process and the discharge process, and that outgassing will consist of water, sulfuric acid, and in some cases hydrogen. So this gas is corrosive, it's explosive, and it's poisonous. Other than that, you don't have to worry about it. And you also are going to use water, which must be replaced on a regular basis. Failure to replace the water is the easiest way to kill a flooded lead-acid battery. Another form of electrolyte is gelled electrolyte, and it's the same kind of chemistry. It's still a sulfuric acid, but it's created in a gel form, and so it's not subject to losing water or outgassing. It's the least cost-effective because it has a higher initial cost. It also has a fairly low number of life cycles when compared to other batteries. And it's similar to AGM in performance for charging and discharging, and it's maintenance-free, and I'd say unless abused. This battery and the AGM both have a vent system built into them, because if you overcharge the battery sufficiently, you can still create gas inside of it which has to vent, or the thing would explode. If those vents ever release due to some kind of abuse, you will still get the outgassing effect, which is why you can't use them indoors. With the AGM battery, the electrolyte is stored or absorbed into a glass mat which is inside of the battery. The performance is better than the flooded lead acid or the gel cell if you take into account the Puchert effect, so you get more usable energy at high discharge rates. They're maintenance free just like the gel cell unless they are abused and you cause them to outgas. They have the longest life of any of the lead acid batteries, about 1750 cycles on a good one, but they do cost more money. That brings us to the lithium battery. The current generation is a lithium iron phosphate battery, called LiFePO sometimes, but it's a special class that's suited to replace the lead acid batteries. For one thing, the working cell voltage is between 3 and 3.2 volts, so it easily scales to a 12-volt battery with 4 cells in series. A lead acid battery has 2-volt cells, so it takes 6 of those in series to make a 12-volt battery. The LiFePO has a higher current capacity than other lithium batteries in terms of its peak output, but it does have a slightly lower energy density, about 14% lower than the best competitor. It also has a very low self-discharge rate, so you can leave a battery like this on the shelf for a year and still come back and have probably 70% or more of the usable energy still in the battery. At that point, a lead acid battery would probably be completely depleted. It is intrinsically safe chemistry, and the negative thermal coefficient discourages thermal runaway. The thermal runaway was a problem several years ago with batteries in laptops. They would develop a short which would cause them to get hot, and the heating effect in itself would cause them to get hotter, and it became a runaway problem and caused a fire eventually. They have a high initial cost, but they have a really good life cycle cost, and they're good for 3,000 to 5,000 cycles. It'll be the highest of any battery technology you can get for life cycle. They are maintenance free to the point you can actually use them indoors. They aren't going to outgas or have any other problems. They do weigh about 25% of the weight of the equivalent lead acid battery for the same usable capacity. They have very flat charge and discharge curves. The flat charge curve means that you can charge them faster because they don't stop taking energy until they get completely charged. It's fundamentally a square law. Your charger can keep on as much current as it can put into the battery within its ratings, and once the battery gets charged, the internal battery management system will simply disconnect. And as you saw earlier, the discharge curves are also flat, so that helps with more efficiency in the inverters that may be hooked up to it. One of the downsides is they do have restricted temperature performance, particularly low temperature when compared to lead acid. They also have a high temperature limit, but it's significantly up there. You're probably not going to run into that. You can't charge most of them below freezing. Somewhere in the range of 25 to 30 degrees is their cutoff point for being able to accept a charge. And you can't discharge them sometimes as numbers high as -4F, or some of them down to -25F now. So here's today's eye chart. And I try to pull into this some different information for you. The wet cell at the top is a really cheap battery. It's inexpensive, at least, and it's sold at Sam's Club among other places, and it's the lowest cost battery I could find in terms of a wet cell battery. It's a 215 amp hour rated battery. Discount that by a factor of 2, so you don't want to go below 50%. And of course it's a 6-volt battery, so you need 2 of them for a 12-volt equivalent. The 3 Trojans are in there because they are what I consider to be a build quality comparable to the Battleborn. It's my favorite lithium battery, and because of that they are more expensive. You will find some cheaper options if you go looking, but it's a very good battery and relatively economical in a lot of respects. There are 3 lithium batteries in there. The Battleborns, I said, are my favorites. And one thing about the useful cycles on that, their literature says 3,000 to 5,000 cycles, but doesn't give a lot of information about the different conditions under which you would measure that, so I simply took the middle point and called it 4. Renogy is different because it measured useful cycles down to a 20% remaining charge or 80% discharge, so I didn't give them the full 100 amp hour rating that the other 2 lithium batteries have. So if you look at that, you can see the cost and the weight, particularly the weight of the lithium is very impressive. You go over through the other numbers, and it's amp hours converted to watt hours by multiplying by 12, and then the number of cycles. The 600 cycles for the Duracell is a guess. They don't publish a rating on it, so I said, well, it's good for maybe half of what a Trojan is. It could be better, it could be worse. But that was the number I used. If you look at the number of times you can charge and discharge and the amount of energy for each charge, you end up with megawatts of potential energy storage in these batteries over time. I converted the useful energy to megawatt hours, and you can see the numbers there. The highest one is the Battleborn. The lowest is the Duracell. I converted that into dollars per megawatt hour by taking the cost and dividing that out. And then I used another column to compare what I called energy parity. If you take the same number of megawatt hours, the 48, that the Battleborns would give you, and then multiply out the cost per megawatt hour, you get the relative cost of the various options. And you can see that far and away the worst choice would be the gel cells, and it's due to the relatively high cost and the very low number of cycles you can get. They're close to the price of a lithium battery, higher than at least one vendor, and they have 1,000 cycles versus 3,500 cycles on that same vendor. This gives you a comparison of relative ranking. You can see there is a wet cell battery if you buy the Trojans. That's very, very close to the cost of the lithiums over the initial cost. You're only paying $672 for the first set, but it'll take a couple of sets to do it, and so you're going to pay another $672 later on. So that's why the life cycle cost comes into play, the energy parity cost. It's a way to calibrate yourself in terms of what your overall cost would be over the life of the batteries if you had to keep replacing batteries until you wore out a set of the lithium battery. And that's really the strongest point, is probably that life cycle costs. They certainly can set you back a fair amount of money up front. Now, disclaimer on this analysis, it's really based on the proper care and maintenance of the batteries. You need to limit the depth of discharge in the lead acid or the Renogy lithium battery if you want to use it. The Battleborns and the SOKs are rated to 100% discharge, where the BMS cuts off before you can damage the battery. So they will last perhaps longer if you don't discharge them as much. Use them in a less critical application. But if you don't maintain the charge properly, or particularly in the flooded lead acid batteries, if you neglect the water levels, they can be destroyed. If the water gets below the top of the plate in a wet cell battery, you're probably going to have a problem with shorting out the cells. That ruins the battery. You could also ruin any of the lead acid batteries by just completely draining it to zero. You can do it in as little as one cycle, but a few cycles perhaps is your limit on that. The internal battery management system in a good lithium battery will protect it from overloads. It'll shut off the output if you try and pull too heavy a load on it. It will shut off if you try to overcharge it, and if your charging voltage is too high. And it will also keep you from operating outside of the temperature limits. So it's a relatively safe system in terms of protecting itself, as it is an expensive investment. The battery shown are certainly not the only choices. They're the ones I am familiar with, and except for the SOK, I have experience of some kind with all these batteries. Not considered as rolling your own. You can go buy all the parts to make a lithium battery. The cells are available, the BMS systems are available. They're not that hard to assemble, though it does take some high current wiring. But if you do it wrong, you can get some really nasty results with high current problems and voltage drops and a lot of heat from the current that's available. So my conclusion was, if the cash outlay is your biggest concern, then the flooded lead acid is the best choice, but you will pay with maintenance efforts and more cost over time. Maintenance efforts are primarily keeping things clean and dealing with watering the cells on a regular basis. Total cost of ownership was the biggest concern. I think the LiFePO are clearly the lowest life cycle costs, and they have other advantages as well. But shopping around, you can find different manufacturers and different outlets for batteries, and they may have different initial costs and different rated life cycles, so there may be other choices out there that you like better, but hopefully doing that chart will show you how to do the analysis to find out the trade-off between initial cost, performance, as well as life cycle cost. This chart gives you more of a qualitative comparison without looking at the numbers so much, just ranks things in terms of the overall effect. And as we said earlier, the initial cost for the flooded lead acid is the lowest, and for the lithium it's going to be the highest. All the other parameters that I looked at in terms of life cycle cost, weight, charge time, discharge curves, putative effect, or maintenance, the lithium is clearly the choice up there. So part of this is a choice not only of the economics of it, but whether or not the advantages of lithium have in other areas are worth the increase in initial cost with a lower life cycle cost. And then I ranked the other ones based on how I felt, where lead acid was pretty much comparable, and then back on the other last two columns, they do have some differences based on that. One footnote: depth of discharge is a very important parameter to consider and to monitor when you're dealing with batteries. And one of the things I want to deal with using terminal voltage as an indicator of charge state for lead acid batteries. And it's very true you can do that, and there's a lot of charts out there that give voltages versus state of charge. What you really must remember, though, is that the terminal voltage in those charts is done after the battery has been allowed to rest. That means not being charged or discharged, and you have to let it rest until the voltage stabilizes. There's a surface charge effect in lead acid that raises the terminal voltage, and it can take anywhere from several minutes to more than an hour to dissipate that surface charge. It depends on the previous conditions of being charged or discharged. Without doing that, the measurement is essentially useless, because you'll be measuring the surface charge, not the actual battery voltage. And without knowing the battery voltage, you really don't know state of charge. So what you really want to do if you're having a battery system, which can be fairly expensive, is you need to monitor the depth of discharge with a battery monitor that measures and then tabulates the current into and out of the battery. It works by putting a shunt in series, usually with a negative lead to the battery system, and it measures what current goes into the battery when you're charging it, and then how much current comes back out of the battery when you're discharging it. That way it can give you a very accurate measure of the physical battery and what the state of charge is, and you can keep from hitting that magic 50% point. It's useful in lithium batteries, but it's essential in lead acid batteries. If you have questions, you can email me those at jim@rv4x40.com, and I'll try to get back to you as quickly as I can. I hope you found today's information useful. If you did, please give the video a thumbs up. If you haven't subscribed already, please click on the subscribe button down below, and if you click on the bell icon, you'll be notified every time we post a new video. I would like to say that none of the information in this video was sponsored by anyone. The Battleborn batteries you see in our coach were purchased by us, not supplied by them. So we have no connection as far as business is concerned with any of these people. Just trying to give you my opinion of some things I've learned over the years about batteries and how to use them and how to maintain them. We'll be back again next week with another video. In the meantime, you be safe out there as you travel around, and if you see us on the highways and byways somewhere in America, please give us a thumbs up and say hello.